Can you guys hear me? That sounds better. Are there usually this few people in class? Okay. Anyway, for those of you that don't know me, my name's Robert. I'm your TA this semester, and I'm handling questions you have about course material that's not in the lab. And then today I'm going to be reviewing an old exam 1. For those of you that aren't aware, your exam is in a week from today. So a few notes. My office hours have always been by appointment. So if you have questions, just email me and I'll get back to you as quickly as possible. If you'd like to set up a Zoom meeting, we can work that out. Next week, next Tuesday, I'm going to have office hours right after class from 10 to 11 over Zoom. And then Wednesday, the day before the exam, from 10:30 to noon. And I'll post an announcement on Canvas with the Zoom link, but this is just any last-minute questions you have before the exam. If you can't make one of these times, feel free to send me an email, and if you have questions, we can set up something else. Some details about the exam, a little different this year, but it can be taken in class or virtually. Regardless if you take it here or at home or somewhere else, it's distributed at 8 a.m. So in class, you'll get a paper copy. If you're taking it at home, there'll be a PDF on Canvas that you can print. If you don't have access to a printer, you can submit a scanned PDF of blank sheets of paper with your work. So just make sure you label your work with the problem number that you're doing so it's easier to grade. There's also going to be a Word file you have to download from Canvas with a problem. And if you're working remotely, you'll have to either print it out and write on it and submit it with your exam. Or if you don't have access to a printer, there's arrows on the Word file, and all you have to do is really drag the arrows and it'll be explained, but it should be pretty simple. And then again, save that as a PDF and upload it with your exam. Are there any questions about that?
So even in class, we'll have to, like if we're doing it in person here, we'll have to scan it?
Yeah, you'll have to scan it when you're done and then submit it on Canvas. So normally the exam ends at 9:55. We're going to give people a 10-minute extra window to submit just in case there's technology issues and scanning and submitting takes a few minutes. Just so you know, for every minute past 10:05 you don't turn the exam in, you lose 2 points. So please get it done on time. And for context, this is going to be a 40-point exam, so if you're 3 minutes late, you lose 15% of your grade just like that. So try and have it done by 9:55, maybe 10 at the latest, and then get it in on time.
I just want to add that you could download it over Canvas in class here as well. We will have paper copies, but then you have to scan it in. So if you get the soft copy over Canvas, you can work directly on the soft copy. So if you're in class, you'll have 2 different modes, but there's the extra time of scanning it in to a PDF. So that's why if I had a choice, I'd probably just download it over Canvas, even if you're in class. And if you have questions during the exam, there will be even if you're live streaming, on the Unite live streaming, at the bottom there's a phone number, and you can call in with questions, and the operator gets those calls, and he'll basically broadcast the question over the speaker. If it requires a private response, which could happen, either Robert or I will go out and answer the question back in the operator's room behind the classroom.
So I have a question. If we're doing this, if we're going to download it, how do we, like you said, there's like arrows or something that we have to draw on it?
Yeah. So there's a Word file with arrows that are already on the file, and you just have to click the arrow and drag it somewhere.
Okay.
So it's...
I get that makes sense, but like I'm not familiar with how to one PDF, like all my notes or whatever, and then I've always printed it off and then scanned it again, because I'm not sure how to add a PDF.
Well, you can do that. There's nothing wrong with doing that if
I
you
don't
want.
have a printer.
What?
I don't have a printer right now.
You don't have,
A printer.
you don't have, oh, but
I'm wondering how to scan in like the rest of your test along with that one.
You can,
if you're in class, you will get a paper.
you can also submit more than one PDF, so you just have to save your Word file as a PDF and upload it with your exam PDF.
Yeah, that makes sense.
Does that make sense? Okay.
If you like PowerPoint, you can, you'll be able to do whatever you want in PowerPoint as well, and just turn it into PDF.
Okay, like Professor Donath said about Unite, there'll be a number to call if you're working virtually. If you have questions and you're in class, we'll be available to answer those as well during the exam period. One thing, if you have trouble submitting to Canvas for whatever reason, if it crashes or something, email me a picture or a PDF of your exam with a timestamp proving you were done before 10:05. If you send me a PDF done at 10:04 though, I don't know, you might have been turning it in late anyway. So just try and have your exam done. If you finish at 10 and for whatever reason you have trouble up until 10:05, we won't take off points for it being late. We'll need proof in that situation that you were done.
And so just to super clarify,
Yep.
if we're in class and we take the paper version, do we or do we not have to scan
You'll
it?
have to scan it.
How do we propose we do that?
Do you have an iPhone?
No.
Okay. I always scan on the Notes app on my iPhone.
So you want us to take pictures of a paper exam and then turn it into a PDF?
Yes, right, Professor?
Yes. I've never had any issues with that in the past, but again, if you feel uncomfortable with that, then just do all your work using the soft copy you download from Canvas, as if you're taking it remotely.
I have a proposal. If you're uncomfortable taking, scanning it as a PDF, I could potentially do that. If you turn in your paper copy, I could scan it for you as long as it's on time. And then, I don't know how that would work really. I'd have to email it to you and then you'd upload it. But if you're really uncomfortable scanning it as a PDF, we can work something out.
There are also other apps for non-Apple. So I use Cam Scanner, for my office.
Is that free?
Yeah, it's free.
Okay. So,
Options just to get it straight to a PDF, and you can send to computers, send to your email, whatever.
okay, yeah, so there's other options. If you have any questions after this, just email me. We'll figure it out before the exam. One other note, you can use any resource you want. That includes your notes, the textbook, the internet even. You can use a programming language, which I used in the past for matrix multiplication. That's totally allowed. All you are not allowed to use or do is talk with another student during the exam. You all know the rule. If you get caught cheating, blah, 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 you could get in trouble with the school. Just please don't communicate with someone else while you're doing the exam. Do your own work. One thing I will note is if you plan on spending a lot of time on the internet to help you solve these problems, you're probably going to run out of time. So you really need to know what you're doing. The internet is just there in case you really need it, I guess, but you shouldn't need it at all. One last note, if you get stuck on a problem, if you don't know how to do a problem, just try and show your work. If you get the wrong answer and you show your work, we'll give you partial credit. Let's say you don't know how to solve a problem and you need that answer for a subsequent problem. Write out the steps you would take to solve that subsequent problem, and you will still get partial credit, okay? So we're trying to give as much partial credit as possible. Any questions before we move on? All right, for the exam content, everything through Lecture 6 is fair game. So that's up to but not including the Jacobian. In my opinion, so I took this class last spring, by far the best study material was past exams. So I put here a little instructions on how to reach the past exams. So there's a folder on the course website with 20 plus years of past exams and the solutions. So if you work on those, you can get instant feedback how you're doing. I will say the most recent, so the past 5 exams or so, are the most relevant. So if you really want to do a lot of exam prep, maybe focus on those. And last thing, if you understand past exams, if you understand the lecture material, and if you understand what's going on in lab, you'll be very well prepared. We're not going to try and trick you. You're not going to see anything you haven't seen before if you prepare. Okay, I'm going to be going over the spring 2021 exam. So this is the exam I took. There are 7 parts, and it's about Eve, which is a full-sized humanoid robot. We're going to be focusing on the right arm of the robot, and there's 6 joints that we're going to be working with. So this is a schematic that the TA made last year for the exam of the right arm and I guess the body. As you can see, there's 3 given coordinate frames. So the A coordinate frame is the robot frame, the 0 is the base, and then down here is the end effector, which is H for the hand, I guess. You can expect something similar in this exam where we'll give you coordinate frames you need, and there will be a detailed schematic with joints and dimensions. So the joints are these dashed lines. You can see J1, J2 in both views, J3, etc. So the first part of the exam asks to find the homogeneous transformation between the body or the robot and then the base coordinate frame. So between coordinate frame A and 0. One thing to note for this exam, for notation purposes, if you see something like this, T sub A to the B, this is transformation defining coordinate frame B with respect to A. And there will be a very big highlighted note on the exam, so you'll know that. You can't miss it. But one thing to note is if you're studying past exams, the 2020 exam had this flipped. So if you see something like this would be defining coordinate frame A with respect to B. So just keep that in mind if you're going through past exams. 2020 was basically the opposite. Every other exam will share the same notation we have here, though. Okay, to solve the problem, there's a 50-degree counterclockwise rotation about the y-axis. Now, if we go back to the schematic, how many of you are familiar with using the right-hand rule to solve rotation matrices? Okay. This is the way I learned to do it. So we're moving from the A coordinate frame to the 0 coordinate frame. We're going to focus on this front view. The right-hand rule, the way I do it, you use your 3 fingers, your middle finger, index finger, and your thumb. We're going to have your index finger be X, your middle finger is Y, and your thumb is Z. So if you want to do this along with me, your index finger is pointing to the left, right? Your thumb's pointing up. That means Y is coming out of the page. As we can see, we're in the XZ plane for coordinate frame A, and we're also in the XZ frame for coordinate frame 0, meaning that there's only a rotation about Y to move from A to 0. Does that make sense? Okay. And as we can see, the rotation is 50 degrees from the vertical, and so that means we're rotating counterclockwise about Y to get Z pointing up and to the left, X pointing down and to the right. Everyone see that? So counterclockwise is going to be positive, and clockwise is negative. That's important. Yeah.
So is that counterclockwise positive, clockwise negative, the same for like the x-axis and the z-axis?
Yes. And the way I learned it, if you're looking like down your finger, sort of, like if you're looking down my middle finger here, counterclockwise is this way. Does that make sense?
Yeah.
It does? Okay. Any other questions? Okay, since there's only a rotation about y, we'll use the y rotation matrix, which is given here. These are all, so that if you rotate about x, you would plug in that angle for theta in x. Since we're only rotating about y, we plug in that positive 50 degrees for theta here. One thing to note, you might run into a situation where there's more than one, you have to do more than one rotation to move from coordinate frame to coordinate frame. So if there was an x rotation and a y rotation, you would solve the x and y matrices and then multiply x times y. So you'd have to do a 3x3 multiplication to get the total rotation matrix. Does that make sense? Okay. And then the transformation matrix, which is what we're trying to find here, the rotation matrix makes up the top left 3x3, and the transformation matrix is a 4x4. So this, where it says rotation matrix, that's the 3x3 we just solved for. The bottom row is always going to be 0, 0, 0, 1. Always. And then the last thing we need to solve for is the translation vector, which is given by px, py, and pz. So we're going to go back to the schematic. So the translation in x is the distance. I'm going to zoom in here a little bit. It's the distance from coordinate frame A to coordinate frame 0 along the x sub a direction. So the dimensions here, it's just given 5. I'm not sure what the units are, but we'll say 5 units from A to 0 along the x direction. So the translation in x is just 5.
P of x then, right?
What was that?
P of x then?
Yes. And then P of y, as if you recall, y is coming out of the page in this front view. So in this side view, it's shown here, y is going to the right. And everything, I think there was a note about this, assume no translation in the ya direction. And all that means is that everything in this left view is aligned vertically. So there's no movement in the ya direction from coordinate frame A to 0. Okay? So P sub y would be 0. And then lastly, P sub z is the distance between A and 0 in the ZA direction, and that's also just 5. Does everybody see that? Okay, great. So the answer then, again, we had the y rotation matrix. We plug in positive 50 degrees, as seen here, and then 5, 0, 5 for px, py, and pz. And then here's our final answer. I see you taking a picture over there. This will be posted to Canvas right after class. Yeah, I understand. I get it. So if you want to use this as a study resource, you can use it as early as today. Okay. Okay. Part 2 asked for the unit vectors, which is denoted by a capital B. And we're looking for the unit vectors from the base frame 0 to joints 1, 2, and 3. Now, the unit vectors are going to be the direction from the base frame that the joints are. And that might be a little confusing, but if we just work through these examples, it should be pretty clear. So you all see J1, this blue dashed line. It falls in the same direction as Z sub 0. So since we're coming from the 0 coordinate frame and J1 falls along Z sub 0, the unit vector is going to be 1 in the Z direction. So we have 0 in the X, 0 in the y, 1 in the z. Does everybody follow that? Okay. Same thing for joint 2. As you recall, y is coming out of the page in this front view. And we see J2 by this point, it's normal to the page. So y0, or J2 is along the same direction as y0. So that's why the unit vector to joint 2 is 0 in x, 1 in y, and 0 in z. Now, from coordinate frame 0 to joint 3, it's a little confusing because joint 3 in this view falls along the horizontal, and neither x or z is in the horizontal direction. So we know, since we're in the xz plane, a component of x and z is going to be in the unit vector. So to get that, I'm going to zoom in again. We see that we need, since J3 is horizontal, we need to find horizontal components for x and z. So for x, we see this angle is 50 degrees just via geometry. And taking the cosine of 50 degrees, we'll find the horizontal of x sub 0. And by that logic, since z0 is 50 degrees from the vertical, taking the sine of 50 degrees, we'll find the component in the z direction. So the answer in x is cosine 50, 0 in y again, and sine of 50. Is that clear to everybody?
So what coordinate frame are we defining these vectors in? Is it the 0 coordinate frame that we found?
Yeah, we're moving from coordinate frame 0.
Okay.
So the joints aren't, right now, they're not associated with a coordinate frame. We're just moving from coordinate frame 0 and finding the direction of the joint with respect to that coordinate frame. Okay, does that make sense?
Yeah.
Any other questions? Okay, if that's clear, we're going to move on to part 3. So when you were asking about the arrows, this is kind of what I'm getting at. The way the exam was done last year, we had to download a PowerPoint file that looked pretty much exactly like this and drag the arrows to define where the origins were. So you can expect something similar to this on this year's exam. To find the origins, the way I learned it, there's 2 rules to follow. So origin sub I will lie on joint sub I plus 1. So origin 1 lies on joint 2, origin 2 on joint 3, etc., etc. And then origin sub I must also line up with origin sub I minus 1. So if you look at origin 1, we know it must lie on joint 2. Joint 2 is this red dashed line and this dot in this view. So we know that origin 1 has to, at least in this front view, has to lie on joint 2 here. And then in this side view, it has to lie somewhere along this horizontal joint. But since we know it must line up with origin 0 as well, it's just going to lie directly, vertically in line with everything else. So we'll see origin 1 right there. Is that clear? All right, origin 2, same deal. It's going to lie on joint 3. So we can see joint 3 is horizontal in the xz plane, so it has to lie somewhere along here. It must line up with origin 1, so it's just going to be directly vertically down from origin 1. And it's the same in this view, this side view. Origin 3 is a little different because it must lie on joint 4, which is vertical in both views. But again, if we know that it must line up with origin 2, it has to actually lie directly on top of origin 2. Is that clear? Okay. Origin 4 is very similar to joint 3 because the joint is in the same direction as joint 3. So origin 4 lies on joint 5 there. Origin 5 has to lie on joint 6, which is horizontal in the side view, and then normal to the plane in the front view. And it's going to lie right on top of origin 4. Now for origin 6, these rules kind of break down because there's no joint 7. We do know that it has to line up with joint 5, or origin 5, my mistake. So it has to line up somewhere with origin 5. And the way I've always done this is that origin 6 also has to line up with the origin of the end effector. So we see the hand origin down here. So it has to line up somewhere vertically with the hand. And since it must also line up with origin 5, it's also going to be in the same point as origin 5. Does that make sense?
No, you have to go back.
What was that?
What is origin 6 pointing to? It'd be joint 7, right? But there's no
Well, that's what I'm saying. There's no joint 7, but there's 6 joints. So there has to be an origin 6.
Okay.
So that's what I said the rules that I wrote kind of break down. We know it has to line up with origin 5, right? Based on this, it must line up with origin sub I minus 1. So the way I learned it is that the final origin has to line up with the origin of the end effector as well. So origin sub H is the end effector. So in both views, it's lined up with the end effector and origin 5.
So why couldn't you put it on OH right there?
Because it wouldn't be lined up with origin 5 in both views, I guess. Or, actually, that's a good question. Origin 6 can't be the same as the end effector origin. There's no joint there, so to speak. So origin 6, I think it also has to lie on joint 6. Is that correct? All right. Is that clear at all? Is that a little more clear?
I guess that makes sense. I was just wondering why couldn't that OH?
Yeah, that's the thing with the last origin. It's a little different, but I mean it should be fairly obvious as well.
And then the reason why joint 3 and joint 4, or origin 3 and origin 2 and 3 or origin 3 is on top of origin 2, why couldn't it be like farther down?
Just because it also has to line up with origin 2 in both views, I guess. So joint 3 is rotating like this, right? In this direction. Joint 4 is like this. If you ever have that, the origins will fall on top of each other. That's just how it works.
So you're saying that, like, I'm assuming this is because when you bend the arm or something like that, then
Because of what?
you bend the arm, they might not be. Oh, I don't know that. That doesn't make sense.
I mean, that's actually a good point. If you bend the arm, they'd have to both be they'd still have to follow these rules. And that's the only point they would follow these rules. If it's not clear, you can reach out to me after class and we'll figure it out, okay? Anyway, moving on to part 4. This was setting up the coordinate frames. And similar to the origins, the way I learned this and practiced this was by following a set of rules. So I always solve for z sub I first. It's the easiest one. It's always in the same direction as joint sub I plus 1. Or another way of putting that is z sub I falls along the axis of rotation of joint I plus 1. So for example, z1 will fall along the axis of rotation of joint 2. Now, if we look at that, I'll zoom in again. In this frame, one thing to note before we go on. We're given here coordinate frame A, and you can see this coordinate frame matches that of the front view, meaning that all of these coordinate frames we're going to solve for the front view of the robot. And on an exam, you'd expect to see a coordinate frame like this so you'd know which view you're solving in. Okay, so like I said, I'll keep the rules there. Z1 will fall along the axis of rotation of joint 2. So in this plane, joint 2 is normal to the page, which means Z1 is going to be normal to the page in this coordinate frame. Okay? So we know it's not going to be either of these arrows. It's going to be coming out of the page or into the page. And we can figure out which direction it's going by solving for y sub I. So the second rule is that y sub I has to be parallel to j sub I. So for solving y1, it has to be parallel to joint 1. And joint 1 is moving up to the left 50 degrees from vertical. So if we can imagine y1 also being parallel from origin 1 here, it would be this arrow moving up and to the left. Does that make sense? And the way the coordinate frame is drawn, if y is moving up and to the left and z is in or out of the page, x has to be this other arrow. So I solve for x by just solving for z and y first, and then using the right-hand rule to find x. One thing I want to make very clear is that in some past exams, you're not given arrows. You're just given coordinate or like origin 1, and you have to draw the arrows yourself, which can get kind of confusing because there's always two possible solutions. So the way the TA did the exam last year, he drew the arrows for you so that there's only one solution, and it's not, I mean, I thought it was easier that way. Even though you're restricted to one solution, you know with the right-hand rule if you're along the right track right away from the get-go. Okay? So like I said, this arrow up and to the left will be y1, up and to the right is x1, and via the right-hand rule, z is coming out of the page then. Does everyone see that?
Why are we saying that that Z is coming out of the page versus like intuitively I would think that Y would be.
It's just, so z always falls along the axis of rotation of the joint I plus 1. Just follow those rules. So if we know the z-axis is along joint 2, and joint 2 is right here in this view, joint 2 is normal to the page, right? Yeah. So z1 has to be normal to the page in coordinate frame 1.
That makes sense then.
Okay.
Rules are really weird, so.
It's just I think these rules are kind of the same as what was discussed last year in the review session. It's how you took these and practiced with them with the exams and got pretty good at it. And yeah, I would recommend doing the same thing. It becomes a lot more clear the more you do it, I'd say. Oh, okay, so I guess I solved for all of them. That's great. Like I said, y1 up and to the left, x1 up and to the right, meaning z's out of the page. I guess we'll look at coordinate frame 2, even though it's already solved for.
Wait, so.
Sure.
I'm sorry. So for O2, joint 3, wouldn't that joint? Oh, we're good. Yep, sorry.
We're good? Okay. Sure. No worries. Coordinate frame 2, again, Z2 has to be in the same direction as joint 3. In this view, joint 3 is along the horizontal, so Z2 is going to be along the horizontal as well. For Y, as we previously said, joint 2 is normal to the page, and since Y has to be parallel to joint 2, Y is normal to the page. And then that just leaves X as the last arrow pointing up. Does that make sense? I'll just do one more. Joint 3, or coordinate frame 3, my bad. Z3 has to fall along the same axis of rotation as joint 4. So again, joint 4 is this purple dashed line going vertically. So Z3 is going to be vertical as well.
So that could, all three there could, or wouldn't Y3 also be X3?
Wait, can you say that again?
So we're talking about origin 3, the box we were just talking about.
Yeah.
That Y3 also be X3, depending on where that rotation is of that fourth joint.
Well, Y3 is parallel to joint 3, not joint 4. Right? So joint 3 is horizontal here. So Y3 has to be along the horizontal. Are you seeing that?
No, I'm not sure which rule you're talking about. That.
We're talking about this rule right here, Y1 parallel to J1. Since we're solving coordinate frame 3, Y3 has to be parallel to joint 3. Okay? Yeah, it's going to take some practice, I think, just like there's rules with I sub I plus 1 sub I. It can get a little confusing. You had a question?
Is there anything besides like the arrows on this page stopping Z from going the other direction? In the same direction?
Meaning
Like right versus left?
for which coordinate frame?
2, I guess.
So that's where there's two solutions, like I said before. So if you weren't given arrows, you could have Z going to the right. But I'm just going to say on the exam, I'm going to give you, if there's a question like this, I'd write out or draw out arrows beforehand. So you're restricted to one solution. But that's a good question. I think we were finished with coordinate frame 3. I think in the interest of time, I'll move on. But again, I'd recommend you all going back and solving this yourself. This exam was really well written, so I think it's great practice for all of you. As long as we're clear on this, we can move on. Okay, one thing, I hope this isn't too confusing. There's an exception to, again, I put these rules up here again. There's one exception you have to be wary of. So I'll go back. In this robot, there's like the joints consecutively are never in the same direction. So like joint 2 is out of the page, joint 3 is horizontal in this frame, joint 4 is vertical. Let's say there's a simple linkage where there's two joints back to back in the same direction. So for this, they're both normal to the page. We can see that this Y2 is it can no longer be parallel to joint 2. That's because rule 1 is that Z is always along the axis of rotation of joint I plus 1. So if we're calling this joint 3 over here, Z has to be normal to the page, right? The thing is joint 2 over here is normal to the page. So now Y2 can't be parallel to joint 2. Does everybody see what I'm saying here? Okay, so there's two exams, 2019 and 2017, that deal with this. And honestly, the way I solve these problems is that you kind of just translate the coordinate frame. Since you know Z is going to be going into the page in both frames, I just translate X and Y over. Does that make sense?
So instead of doing all the stuff that you had previously, like finding the X, Y, Z and stuff, you just do a pure translation?
Yes. So this is, like I said, this is just an exception where these rules, the only rule that applies is going to be the Z, because it's always along that joint. But yes, in a way, they just translate over. And if you want to see that again, 2019 and 2017 has problems that deal with that.
The parallel case?
What was that?
I remember like we have covered something about like two axes being parallel.
Yeah, this is exactly that. This is just something to keep in mind when you're studying, though. So don't be super religious to these rules if you see a case like this pop up. But the one thing, Z sub I will always fall along the axis of rotation of joint I plus 1, always. Okay, next part, we're going to fill in a DH table. I'm just going to tell you, you need to know how to do this. It's part of every exam. You're going to need to know how to do it. Same thing, there's 4 rules for DH tables that I use to solve these. And I always start finding theta, which is the rotation about the z sub I minus 1 axis from coordinate frame I minus 1 to coordinate frame I. And the first time I heard that, I got really confused. So I don't blame you if you're confused. But it's really not too bad when you really look at an example. So I think, yeah, we're gonna start with joint 1 and find theta for joint 1. So I still have the rules written up here. You can follow along. And you use your coordinate frames to solve the DH table. So I pasted coordinate frame 1 in here just to make it clear. So again, right-hand rule, we see we're going from coordinate frame 0 to coordinate frame 1. So for coordinate frame 0, your thumb is Z, it's pointing up and to the left, X is pointing down to the left, Y is coming out of the page. We need to rotate about Z0 to get, that's the theta. And the goal of this rotation is to get X sub I minus 1 parallel with X sub I. And that might also be kind of confusing, but if we see x1 that we solved for in coordinate frame 1 is up and to the right, we need to rotate about z sub 0 to get x sub 0 in that same direction. Okay? So if we rotate about z0 180 degrees, the x is in the same direction as x1. And we show that here. After the rotation about z0, 180 degrees, x0 moves from going down and to the left to up and to the right. And now it's parallel and in the same direction as x1. And the reason we need to get x sub I minus 1 parallel to x sub I is because the next step is finding alphas, which is a rotation about x sub I minus 1. So if we don't have the x's in the same direction in parallel, we won't be able to rotate about the x-axis and get the coordinate frames to line up, right? Does that make sense? That was a lot. Question?
So when you were finding the origins, like previously, or the coordinate frames, and you did that second solution, then you would just, it would be like a 0 rotation?
Yes. Yeah. There's cases where you would have just 0 and 0. Then it's just a translation, and that would, you'd see that in the DH table. We'll go over that in a bit. If there aren't any other questions, again, we rotated about z sub 0 180 degrees. Since it's 180, it doesn't matter if it's positive or negative. It's all the same. Now again, right-hand rule, if we have coordinate frame 0 now oriented like this, where z is your thumb up and to the left, x is your index finger up and to the right, we need to rotate about x sub 0 to match this coordinate 1 frame. So if we rotate, this part's going to take some practice, just so you know, but if we rotate 90 degrees counterclockwise about x sub 0, now we have our middle finger up and to the left, index finger up and to the right, and we match coordinate frame 1. Does everybody see that? So in our DH table, we'd say for joint 1, okay, I just had that, so we paste in, and this coordinate frame now matches what we need for coordinate frame 1. So for joint 1, the rotation about z0 was 180 degrees, and the rotation about x0 was 90 degrees counterclockwise, so it's positive. And one thing you can do if you see a DH table on the exam, you can write in theta 1, theta 2, theta 3, etc. for every joint. And that's because these thetas represent the actual joint angles of the robot. So a lot of times, like in this, like what you were saying, if the arm was moved at all, the joint angles would not be 0. In this instance, they're probably going to be 0, and we will tell you if the joint angles are set to 0 or not. But that's why you need to write in theta 1, theta 2, etc. Okay, everyone understand that? Okay. Then I have all of them solved for here. I think we'll do one more, and then the rest of them you guys can solve on your own. Again, I'd really recommend that. For joint 2, we're going to, again, right-hand rule with our fingers oriented the way coordinate frame 1 is. So middle finger up to the left, index finger up and to the right, and we need to rotate about Z to get x1 and x2 in the same direction. So x1 right now up and to the right, x2 is vertical. So I see you're doing it right there. Yeah, if you rotate about Z 40 degrees, because I don't have it here, but this angle is 40 degrees. If you rotate counterclockwise about Z1, now x1 and x2 are in the same direction. So theta 2 is going to, theta for joint 2 is going to be 40 degrees. And then for alpha, now x is pointing up. We need to rotate about x1 to get to coordinate frame 2. So since we want Z going to the left, we'd rotate 90 degrees clockwise about x1, and now Z is going to the left. So alpha is negative 90 now. Does everybody see that? Again, this is really important, so if you have questions, let me know. If not, we're going to move on to solving D and A. And they're already solved for. Okay, so D sub I is the distance in the Y sub I direction from origin I minus 1 to origin I. So similarly, it's a lot of verbiage that can be confusing, but if we actually look at the diagram, it's not so confusing. I'm going to zoom in here. I dropped coordinate frame 1 and 2 onto the diagram to make this easier. But if we're looking for D1, we need to find the distance between from origin 1 to, from origin 0 to origin 1 in the y1 direction. The problem with this is that y1 obviously is not, it's not moving, it's not horizontal, it's not vertical. So we can't just call it a straight translation or 0. It's at an angle. So y1 is 50 degrees from vertical, which means let's see. And since origin 1 is horizontally moved from origin 0, we'd multiply the distance between them by the sine of 50 degrees, since it's 50 from the vertical. Is that clear? Okay, and then by that logic, we can find A sub I. It's the distance in the X sub I direction from coordinate frame I minus 1 to coordinate frame I. So for this one, we move from origin 0 to origin 1 in the x1 direction. The thing to note about this is that x1 is kind of pointing back towards coordinate frame 0. Not exactly, but it's in that it's pointing towards the right at some angle, and we're moving to the left to go from origin 0 to origin 1. So if that ever happens, there's going to be a negative sign in front of A. So just like we did for D, D is 9 times 9 is this distance. 9 times sine 50. A is going to be 9 times the cosine of 50. But we need to include that negative because the direction x1 is in a way pointing back at origin 0. So remember, we're moving from origin 0 to origin 1. Okay? Does everyone get where I got that negative from? All right, I'm going to do one more D and one more A. And the rest of these are pretty simple compared to joint 1. So if you understood that, that's good news. So D sub 2 for joint 2 is the distance in the y2 direction from origin 1 to origin 2. So we see origin 1's here, origin 2's here. And I placed x2 and z2 like this, and we solved for that already with the coordinate frames. So if x2 is up, z2 is to the left, we know y2 is into the page. And since these two origins are lined up perfectly vertically, there's no distance between them in the y2 direction. So D for joint 2 is just 0. Now for A2, we're going to move from origin 0, or I'm sorry, from origin 1 to origin 2 in the x2 direction. And this is similar to, for joint 1, x2 is pointing back towards joint 1. So we're going to move 5 plus 10, so 15 units from origin 1 to origin 2. But since we're going in the direction of x2, it's negative 15 because x2 is pointing back towards origin 1. Is that clear? Okay, great. Similar thing, I'm going to let you guys solve D and A for the rest of the DH table on your own. It's really good practice. The next part of the exam is solving A matrices. And if you see these on the exam, you should be pretty thrilled because this is just plug and chug. And what I was saying about the joint angles, here we say assume the joint angles have all been set to 0. So that means theta 1, theta 2, theta 3, up to theta 6 here, just set to 0. So now theta I is just 90 degrees. There might be a situation where we say theta 6 is, I don't know, it could be anything, 15, 30, whatever, and you just put whatever value it is in for theta 6 and add the two together. And then you take your thetas, your alphas, D and I, and just plug those into this matrix. And when you do that, one thing to note, if you see like A subscript 5 to the 6th, that's like this, so I is 6. So you take the values of joint 6 from the DH table. Same thing, A 6 to H, you take the values from H.
Does that AI I minus 1 matrix ever change, or is that just set in stone?
Set in stone. So again, if you don't have to know this, just have it written down somewhere for the exam. If you indeed have to fill out A matrices, just follow this directly. If that's clear, we'll move to part 7. So part 7 asks to find the transformation matrix from coordinate frame A to coordinate frame H, which remember is the end effector. And we're assuming that the transformation matrix from A to joint 5 or to coordinate frame 5 is already given. So if that's given here, all this is simple matrix multiplication. So to get TAH, we'd multiply this TA5 transformation matrix with the two A matrices we just solved for. So the way matrix multiplication works is you see a 5 up here and a 5 down here. You can cancel those, so to speak. So if you cancel the 5s, cancel the 6s, you're left with an A and an H. And that's really how you'll know if you did this properly. It's what you're left with. For this problem, you are actually required to do 4x4 matrix multiplication 3 times. So it's important to know how to do that. If you're familiar with MATLAB or Python or some coding, I'd recommend writing a script beforehand where you can just plug in values for 4x4 matrices and then multiply them together. That's what I did, and it probably saved 5+ plus minutes. So if you're worried about time, maybe do that beforehand.
I know on Google, and this is for other people who don't want to do MATLAB, but
Yeah.
like 4x4, you just like multiply 4x4 matrices, and then you could just do TA5, and then T5A, and then A65.
Can you speak up?
Sorry.
Really hard to.
I mean, so what you're saying is, could you just use Google, like a Google 4x4 multiplier? Yeah, you can do that. I mean, the internet is, like I said, you can use it. One thing, if you don't want to use MATLAB, that's fine. One thing I found helpful is if you're going to do that on the exam, do that when you're studying. So I mean, it's probably right, but if you write your own script, make sure it's working properly with practice exams before using it on the actual exam.
Then you should be able to just do T5A and then multiply A65, and then whenever you get there, then multiply AH6 then, or is it the other way around?
I mean, you can say it however you want. I say TA5, A56, but whatever is clear to you. Just know that this notation is important, right? So 5 in the, I guess, at the top means we're defining coordinate frame 5 with respect to coordinate frame A. That notation is important. You can call it whatever you want. Okay? Is this all clear? Great. We're going to skip problem 2 from the exam. It was a lot of writing, I guess. I mean, I'd recommend looking at it, but for our purposes, I don't think it's worth going over. We're going to look at roll, pitch, yaw, which from when I took the class, I know was kind of confusing for some students. So I haven't got any questions on it, so if you guys all understand it, that's great. But part 1 for this problem asks to find the roll, pitch, yaw angles from the UR5 base coordinate frame to the tool, so up where the gripper is. This is the same robot used in lab, obviously. The first part asked for the Z, Y prime, and Z double prime angles. These are the Euler angles. So if you ever see Euler angles, that's what this is referring to. One way that I found helped me to solve these problems is that the Z, Z prime, and Z double prime axes, if Z is vertical to start, the Z, Z prime, and Z double prime axes will always be vertical. Y, Y prime, Y double prime will always be in the same direction. They could be, the arrows could be flipped, but they'll be in the same line, I guess. Same with X. And what you do here is once you do a rotation, you have to, so I do this using right-hand rule again, but you have to rename your fingers, I guess. So I'll run through this. If we start in this first frame, Z is the thumb, it's pointing up, Y, I guess, up to the left, X up to the right. The first rotation has to be about Z. So here I rotate 90 degrees counterclockwise about Z. So we get here. Now, the index finger is pointing in what was the Y direction. So we have to rename the index finger Y prime, even though it was X before. Does that make sense? And now the middle finger used to be Y. We're naming it X prime. And Z hasn't changed, so the thumb is still Z prime. Okay?
Can you explain how you got from 1 to 2 on that first one there?
Like how I knew it was 90 or just how I rotated?
There's something wrong.
There's something wrong?
How did it be 180, or
Well,
how did the X flip and Z stay upright?
Okay, that's what I'm trying to get at here. When we rotate 90 degrees about Z, you're right that it looks like it rotated 180 because X prime is opposite what X used to be. But that's where you have to like rename your fingers. We rotated 90 degrees about Z. Now your middle finger is where X prime is, right?
Yeah.
Okay. So when I said Z, Z prime, Z double prime all will remain vertical, Y, Y prime, Y double prime will always remain in that line. So when you do a rotation, y prime has to be in the same direction or be parallel to what y was. So even though we rotated about z and now your index finger is in that direction, our index finger is now y prime.
So x became y prime.
Yes, exactly. And y became x prime because your middle finger is now pointing along what used to be the x direction.
Hold on though, if we cross, even if we change this, we should still be able to cross x prime with y prime and get the direction of z prime, right?
Yeah, and Z prime's going down.
These z prime should be pointing down then, which can't be the correct. Because z prime should be z, since our first rotation is about z.
Okay, that's a good point. I guess the way I think about it, you're always crossing your middle finger and your index finger to get your thumb. And when you rotate about z, you're still crossing your middle finger and index finger to get your thumb.
Is x prime only going, why is it x prime not going like up and to the right then? Because if you rotate 90 from here, x, or I guess down to the right almost, you know what I mean? Like, that's, maybe I'm looking at it wrong. I feel like something should be going up and to the right if you only went 90 degrees.
Well, you're rotating 90 degrees counterclockwise about z, so you'd be doing it like that. See what I'm saying?
Well, then it's positive 90, isn't it? Oh, never mind, right around. You're good.
There's one thing I'll say, there's always two solutions. So like you said, you could rotate negative 90 degrees about z, and you'd still have to figure out how to get to this end result. But there's two solutions. I had a feeling this would be kind of confusing. Who's confused about this? Okay, that stinks. Again, this is just the way I learned how to do it. If you know another way to do y or z, y prime, z double prime, you can do it that way. You'll still get the right answer.
So why does y have to stay parallel to each other? That's what doesn't make sense to me.
That's just how I learned how to do it. Okay, you just, when you rename your fingers, y prime is going to be parallel to y. That's just how I learned it. Yes.
For the sake of that, say you go 42 degrees about z.
Sure.
What do you do then?
When you do roll pitch yaw, I've only ever seen examples where you're rotating 90 or 180 degrees. I'm not sure about that one.
Well, that's what doesn't make sense
Professor Donath, do you have anything to add that would help them out?
Well, the thing is, to be honest with you, I have a different convention for pursuing it, and that's why I don't want to confuse everybody with a different approach.
Can you maybe explain your approach? Because this is not working for a lot of us. So.
Well, essentially, ZYZ, we're talking about rotating 90 degrees. Let's say the palm, you'd have to look, I'd have to go up front so people can see me. Why don't I come up front?
Would it be okay if when I'm done, you come up and re-explain this problem?
Finish the whole thing and then I'll go back.
Okay, my apologies if this is confusing. This is the way I learned it last year. I understand if it's not working for some of you. It's kind of counterintuitive. Hopefully, Professor Donath's method is a little more intuitive or easier to understand right away. But since he's going to run through his convention after I'm done, we're going to move on to the second part of this problem, which was roll, pitch, yaw, but using the UR5 convention. And this one is way easier. It's just rotation about X, then Y, then Z. And you don't have to do any of this renaming stuff with your fingers. You just rotate about X, then Y stays the same. You rotate about Y, and then finally Z. So I'll run through my first solution, and hopefully this makes sense. Using my right-hand rule, if you rotate 90 degrees counterclockwise about X, now Y is pointing down, Z is up and to the left. And then then you rotate about Y, and one thing about rotating about Y, you want your Z coordinate or your Z direction to line up with what it has to be at the end, because your last rotation is going to be about Z. So in order to do that, we have to rotate about Y 180 degrees. And then Z is lined up with what it's going to be at the end. And it just so happens for this example that we don't have to do a rotation about Z because it's already in the correct orientation. And this is going to take practice too, because it's like you might be wondering how I knew to rotate about 90 right away. It's kind of just after a while you'll look at a coordinate frame and see, okay, like I just have to do something like this, and you can just figure it out on your own. But at some point, if you practice enough, it becomes pretty instinctive.
Why is it 90 and not negative 90?
Because, like, let's say you're looking down at the Z axis, right? Z is pointing up. Wait, excuse me?
Z is going there, that way. And then now we want Y to be down here. Are we?
He's,
You rotate about X first.
Right.
Yeah.
If you rotate about the X 90 degrees, wouldn't that make your Y axis going up?
yeah,
Oh, so it'd be negative 90 about X, is that what you're saying?
Yeah, I think for solution 1 and 2 it's flipped.
Okay. Yeah, actually, you're right about that. It'd be negative 90 about X. It's clockwise. Thank you for pointing that out. I got these answers from last year's exam. So is there a problem with the exam? But you're right. Thank you. This is actually a negative 90 degree rotation, and then 180 degrees about Y. And that gives the right answer. As long as everyone sees that, I'm sorry about that. Again, I took it from last year's exam. I'll change that before I post it to Canvas, though. Okay? Are there any questions about anything else other than my confusing roll, pitch, yaw convention? I'm going to stick around for Professor Donath's convention so I can learn it, and if you have questions, you can ask me before the exam. Okay? But that's all I had. So, yeah, thank you guys for listening, and yeah, thanks, man. Anyway, Professor Donath, you want to come up here?
Basically, I'll be very honest with you, since the TA is involved in grading, and in fact, Robert and I have been working on the exam that you're going to be getting a week from now, and we basically reverse engineer a robot in order to come up with a new and exciting example for you to work through relatively the same kinds of issues in this coming exam as you had in previous exams. This exam, Sam Scherzer was the teaching assistant last year, and he and I worked on this robot, on the robot you saw before for quite some time. The idea here, essentially, and I prefer to use my hands, my arms, rather than my fingers. And so essentially, and part of this is in any application, there are many different ways to get from the starting point to the end point. We're giving you the end orientation. We're telling you what the start orientation is. And you just have to work your way through it. And I'll tell you right now, you are going to guess a few times until you find, aha, eureka, I have a solution. So in this particular case, following what I see here, since I haven't spent all the time on this as Robert has, if Z is pointing up and is my head, and this is X, and this is Y, so this is Z, X. I wish I had a letter X in my hand. Let me just hold this and call that X. All right, this is Y, that's my head. So essentially, we're starting off at the base coordinate system, which is Z pointing up. So let's just assume that X is this way, Y is that way. And let's say we were following the path that's on the screen as I see it. 90 degrees about Z is this kind of motion. Do you agree? Okay? And then the minus 90 about Y. Remember, this is now Y. Okay? So positive 90 would be this way. Have I got that right? 1 second. No, I'm sorry. You're right. Okay? Positive 90 would be this way. Negative 90 would be that way. So that means X would flip up, correct? X would flip up. This would still be my Y, right? And Z would be pointing back, right? And then the next would be, I'm just following what it says here. So we just did 90 about Z. Now we did minus 90 about Y, which is back like that. And then the next step, it says here, is to do 90 degrees about Z prime, okay, which is 90 degrees about Z prime is this way, okay? And how does that look? Does that come out?
So you're just leaving, you're still keeping them X, Y, and Z. You're just adding a prime for each.
Correct. Each step puts a prime on it. That's how I do it. I don't rename anything. I simply follow step by, every time I do a step, I name it prime. Do another step, double prime. Set?
And then the roll is along the...
Okay, the first step, remember what we said, yaw is always a rotation about a vertical axis. If you think about it, we talked about this. If I have a horizontal axis and a vertical axis, in this case, we do have that. Z is pointing up, and the horizontal plane is defined by x, o, y. X, so in this particular case, Z is up, x and y. This is a horizontal plane. Z is a vertical axis. Yaw, in my thinking, this is yaw, rotation about the vertical axis. I always know what the yaw is, and remember what we talked about, pitch. Pitch is going to be a rotation about y. Whatever the new y is it's going to be either a rotation down or a rotation up. Yes?
So are you always going to rotate about 90 or negative 90 degrees? Or
No, not necessarily. There may be other angles involved. In this particular case, why should there be additional angles when the final orientation is orthogonal and is parallel to the original? So there's no need to add. But as you saw in the problem number 1, yes, there were some angles that were kind of weird. And to be honest with you, I liked it being weird for an exam problem. But we made it 45 degrees. It wasn't that totally nutty. And I can tell you right now, that robot was somewhere on the web. I don't know if it still exists. I think I saw some reference to it recently, but it happened to be a good example to work through the details.
So I have a question then.
Yes?
I mean, this all makes sense when you say that, when it's perfectly 90 degrees or whatnot, but so say if we have like we have a yaw of like 45 degrees and then we do a pitch of another 45 degrees. Now if we wanted to make a roll, is it still along that original x-axis then?
Yes.
Okay.
So essentially,
Everything's based off of that original x.
correct.
Okay.
Correct. X, Y, Z. All right, so for example, it might be that I just do 45 degrees, okay? Then a rotation about Y. All right, so positive Y, that's going to be my pitch. And then roll is going to be, again, about the last Z.
Oh, no.
Well, here we go. Again, the first step is yaw, right? About my head, right? That's going to be the first step. This is X, this is Y. The second step, again, we're talking Euler angle, so it's about the Y, right? So your right-hand rule, your thumb follows the Y. So positive would be this way.
Yeah.
Agreed?
And then why wouldn't it be along your x now for roll?
Because this is a different convention. This is essentially the ZYZ convention. Roll, pitch, yaw can be defined differently. And in this particular case, we're doing rotation first, Z, Y prime, Z double prime.
Okay.
So Z, first rotation, this is X, this is Y. Second rotation, this is about Y. All right, now Z is pointing along this direction, and that's where the roll is.
Okay, so it's just depending on how you define.
Yeah, the textbook actually does describe both different ways. They say, but the term roll, pitch, and yaw is referring to different angles.
Okay, sorry, that was just really, for me it was confusing because it keeps changing back and forth.
Well, I can tell you when we first started using this particular robot, I was also confused by the robots convention. And I then did notice that the textbook worked out both. They had the ZYZ, and if you go back and look at my notes, you'll see where that section is. And then just a little bit later, they do the XYZ. Okay? And it's just a different, again, different conventions. If you think those are the only two conventions, look at RoboDK, and you can flip through a whole variety of different conventions that they worked out for all these different robots that they capture in RoboDK. Yes?
So, like you said before, so XYZ, XYZ prime, XYZ double prime, they all, like each axis lies in kind of the same line, right? But then you just rename, for the XT, YT, ZT, you can just kind of rename them to like whatever you kind of need them to be the final origin.
That's right. I'm not talking, there's no translations in my discussion, okay? There is obviously a translation from the position of the origin down at the bottom of this robot all the way up to where the tool is up on top. But again, every manufacturer, how they line it up, and how they decide and what they decide, I haven't got a clue how they come to that decision. Somewhere along the way, they come to a decision which says the tool coordinate system shall be this. Always, and I haven't yet seen, but if I have a gripper, the Z is going to go through the gripper. You know, it's going to be normal to the gripper, the approach vector that we talked about. And if you look at it, they do follow the convention that I've always used, is that the Y is going through the direction of the gripping. So when the two teeth or the two fingers come together, that direction is going to be the Y. So if this is Z and this is Y, X is normal to the other two. So can you see where my cursor? Yeah. So essentially, this X, Y, Z sub T coordinate frame is not unlike what I've discussed in my examples in my notes. There's nothing wrong with this origin. They decided on it. And it's just a question of how you define roll, pitch, and yaw. Whether you follow the ZYZ or the XYZ, you'll come up with different angles. Again, the roll, pitch, yaw definition that's associated with the UR5 is going to be different than ZYZ, because they don't use the ZYZ.
So in this instance here, they're saying roll is just the rotation along the regular z-axis, right?
About the latest z-axis.
What do you mean the latest?
Again, if I go through 3 steps, the first step is a rotation about z, right? That's yaw. The second step is a rotation about y, which is pitch. So that's yaw, pitch, and then the roll is the rotation about the latest z, which is a rotation about my head. Z double prime, exactly. The primes are to tell you what step in the process you've gone through.
How many of you think that's more intuitive or easier? Okay, I'll tell you what, I'm going to make a slide and add it to the presentation about Professor Donath's method. So if that's easier, you can study using that. Okay? So this will be uploaded later today.
Thank you. This exam that you're going to be working on a week from today is going to be very interesting. I can tell you that. Robert and I have worked on it for weeks and put in hours.
Yeah.
Right?
Yeah.
Okay. All right. Why don't we take a 10-minute break so people can get some liquid refreshment or visit the restroom. Wait a minute. Isn't this your laptop?
That is my laptop.
Please. And check it again, you know, check your result with mine and see if that matches up, okay?
Yeah, I think there might have been an error on last year's exam.
Well, we'll find out.
I guess so. All right.
If so, you know, when nobody complains, I have to assume there isn't a problem.
Yeah, I guess we'll see. We'll find the same error.
Yeah.
All right. Cool.
So let's pick up. I'm sorry that I'm moving so slowly. I slipped on the ice last night and really whacked my left hip. So so if I'm moving kind of weirdly, that's because of that. So I haven't had time yet to go check it out. So what we're going to talk about, and the other day we looked at vibratory feeder bowls, we looked at conveyor belts and flip stations. I'm not going to get into any of that. I also mentioned this new company, Right Hand Robotics, which has some really interesting solutions for being able to pick parts out of a bin, which has always been a problem for decades. And they seem to have a pretty interesting solution. Again, do take a look at it. Just do any search or go look at Right Hand Robotics. They have an interesting website. So I don't want to spend any time on that. I did talk about it the other day, and so I won't continue on that path. What we are going to do, and we're going to spend more time on coordinate frames, and we're going to spend quite a bit of time on this particular problem, which is picking up a pin off of a table. And I can tell you right now, it's not in the textbook. Okay? This is material that I adapted from a 1980 something or other textbook, and I looked it up this morning, and this is pretty heavily adapted, so it's not the same, but it does pick up on some of the issues. I like this particular problem because whether you're using the UR5 robot, a Puma robot, or any one of the A, B, and B robots, UNESIA robots, and we can just go on and on for Nook robots, this is not an atypical problem that we want to pick up an object off of a table. And in this particular case, we want to pick up this pin that you see over here, and we want to stick it into a hole. All right? The hole is defined with respect to a block. So here we have a block. The block has a coordinate system. And arbitrarily, x, y, and z, it still follows the right-hand rule. Y is x up and z, it doesn't matter. The whole point is to create coordinate systems to look at a particular set of examples. We have a robot with a stick figure for the robot. The stick figure shows that the robot's base coordinate frame has z pointing vertically and then x, y in the plane, in the horizontal plane. And then we have a conveyor belt, and somebody defined the x, y, z of the work table or the conveyor belt. You can consider this a workbench as well. It doesn't have to be a conveyor belt. It's just there as an example. And then we have a pin. And we have a gripper that's going to come down from overhead. It's going to come down and pick up the pin. So in other words, the two fingers have to come down, and they should be parallel to the axis of the pin, and they should be able to close on the pin, and then it's going to leave the surface and then swing around in order to stick it into the hole in the block. And so we are going to create a whole bunch of coordinate frames, many more than you are ultimately going to need, but I want you to see all the pieces that end up being simplified greatly, okay? And the reason for having all these different coordinate frames is we don't know in advance what the end effector will be. We don't know exactly. We're designing a robot, and we're designing a syntax of a language, or whether you're using a teach pendant, or whether you're using any other kind of system for programming the robot. We're trying to create a generic way that can handle all the different possibilities that might exist in the future. So we are going to step through all of these, and we're going to follow these coordinate frames. And so what we're going to be doing, again, insert the pin in a block. And we are going to have, let me make this a little bit smaller. We are defining many more coordinate frames, and what you see here looks like vectors. They don't look like homogeneous transformation matrices. You don't see any orientation coordinates because it would be such a jumble you wouldn't be able to figure anything out. So what you're seeing here is just the center of each of the coordinate frames as we move through. So for example, we have an object, generic object that we're going to want to pick up. All right? We're calling that OBJ, and that's the coordinate frame with respect to the O, the base coordinate system. There's OBJ, and all we're drawing is a vector. There is clearly attached to the point at the end of this OBJ vector, which is a P, there's an X, Y, Z to it. There clearly is also a coordinate frame that goes along with it. And we'll take a look at how that coordinate frame should be oriented. Then there may be a feature on the object. For example, that block has holes in it. So there may be many holes in that particular block. And then each feature on that object may have a different position and a different orientation associated with it. So that's what the F is. Now, let's step back. What is Z? Z is going to be a homogeneous transformation matrix that is going to take us from the world coordinate system, the workbench coordinate system, whatever we want to call it. That's going to be essentially, Z is going to take us to the base of the robot. So notice, here is the manipulator's base coordinate system, which is going to be over here, wherever it is. And then we're going to have T6 here. T6 is ultimately going to be a 4x4 matrix, which is going to tell us where the flange of the robot is in world coordinates. All right? And T6 is going to take us out to the coordinate system of the tool, of the gripper, of the end effector. And that end effector is E. Now, we're also going to have something called G, which we're going to look at very carefully. And G is going to allow us to basically help us define the orientation of the end effector with respect to the object. Now, that sounds very cloudy and blurry, but we need to look at an example and work our way through it, and you'll see what I'm talking about. But the bottom line is, whenever we have a pin, and I'm holding the pin, when I'm doing that, and here's my gripper is my tool, and I'm holding it in a certain position, essentially, assuming the world coordinate system is the workbench over here, Z is going to take me out to the base of my robot. Let's call it the shoulder here. So Z is going to take me to the base of the robot. T6 is going to be for a 6-jointed robot. There may be 6 joints. It's going to take me through the DH parameters all the way out to my end effector, the flange of the end effector. That's essentially T6. And then I'm going to have E, which are coordinate frame associated with the tool, with the end effector that's going to come out of the flange of the robot. But when I pick up a part, this object, and let's assume the object and the feature, that's really the pin over here. Okay, there's a coordinate frame associated with the pin. That coordinate frame could be aligned with the major axis of the pin. There might be a right angle to that pin. And here's my fingers, and they're going to have to mate with the pin. And we have to make sure that if I work out the equations from here through Z, through T6, through E, it is going to equal to the object, which is a coordinate frame going to here, through the pin, and they have to, the orientations have to be exactly the same. Now so be patient, and we're going to go through this pin problem, and I'll show you all the coordinate frames and what matches up with what. So here is the task sequence we're going to work through. The first step is we're going to move to some position over the pin. Okay? Then we're going to move down from overhead And we're going to make sure that our fingers don't yet touch the pin, but we want to make sure they're parallel to the pin so that when we close the fingers, we are closing it around the pin at an appropriate location on the pin. And we'll take a look. What do we mean by appropriate? All right? We'll take a look at that. We're going to grasp. It means we close our fingers around the pin, and then we lift the pin vertically away from the tabletop. And then, assuming there's a big block over here, and there are holes in that block, we're going to spin around, move around, and then I don't have a block, but I'm going to assume that there is a hole over here, and I'm going to come around to this side, and I'm going to want to a position and orientation which is aligned with the shaft of the hole. And then I'm going to insert the pin an appropriate distance into the hole, let go, and then move my arm away. And then I could start the whole process again. Okay? That's what we're going to look through step by step from beginning to end. Okay? And I'll show you all the coordinate systems that we're dealing with. Hopefully you'll get it. Okay? So, and we'll break everything down, and we're going to give all these different coordinate frames. Let's say there's the position and orientation, and as we've said before, when we talk about a position and orientation, we call that a POSE, a pose. The pose is the combination of position and orientation, and P is going to be the pose of the pin in the base coordinate frame. See this pin? P is going to be, if this is the base coordinate frame, P is the position and orientation of that pin in the base coordinate frame. You can decide what that should be, and we are going to make an assumption. And then I'm going to show you that that assumption may not make a lot of sense, and there may be a simpler way to do it as well. So we're going to do that. The block is sitting here, and the block's coordinate frame, again, is defined B with respect to the base coordinate frame. There are going to be holes in this particular block, and they're defined with respect to the block. Remember, somebody designed the block, and there's a CAD diagram somewhere which defines exactly how deep the holes are and defines the tolerances and the distance between them. So those are essentially the position and orientation of a specific hole. And there may be, I don't know how many holes, but this would be the ith hole with respect to the block's coordinate system. And then we're going to talk about the pose of the gripper. Okay? The position and orientation of the gripper, but it's when holding the pin, and we're going to see that it's with respect to the pin, and you're going to wonder, heck, why do we have that here? And we're going to see that that's going to simplify a lot of things. So PG is the position and orientation of the gripper with respect to the pin. Okay, with respect to the pin. PA is the pose of the position and orientation above the pin from which we're going to approach. If we want to move the pin to some other location and not go back to PA, we can define that as PD. But notice, PA is with respect to the pin. PD is also with respect to the pin. And then if we have these holes in the block, essentially PHA is going to be a coordinate frame. If this is the hole here, PHA is some position and orientation along the axis of the hole, and it's the place we first go to, position and orientation, and then we slide the pin into the hole. We slide the pin into the hole by a certain distance, and again we're going to define those distances. And once we're into the appropriate depth, we let go of the pin and go back and go get another pin or whatever else the next task is. Okay? So PIN is how deep the pin is going to go in, and that's with respect to the hole's coordinate frame. So we're going to go in, you know, again, that's defined by the task itself. So this is what we're going to look at. And the most important part of everything is to start off by defining the pin and writing all the equations down. So essentially, what you're also going to do if you are picking up a flashlight part, which is coming up not in the not too distant future, you know, where is that part in the real world? Now, clearly, when you're using offline programming, you can do anything you want to. It's all it is software. But when you get into the real world and you have a real flashlight and real parts that you have to pick up, they may not be exactly where you thought they were. Yes, the CAD program that you were given said it was here, here, and here, but when you get down to it, it may not be entirely there. And so typically, you're going to start off by just getting your gripper down to these objects and touching them. You know, getting down there and closing on them and seeing that you are indeed touching them at the right places that you need to. Okay? If you're too far to one side or too far to the other side, you're going to move the item. Okay? Or you're going to cause an issue. How many of you have done machining? Oh, well, a goodly part. If you're a machinist, okay, and you need to cut off a very accurate, you want it's a lathe or a milling machine, doesn't really matter, and you're going to basically remove a certain amount of material, and you want to be sure you're removing only that much material, how do you know where the surface of the part is that where you're going to start the cutting action? Anyone? What do you typically do as a machinist who has 10, 20, 30 years of experience?
Well, it depends on
What?
It depends on what kind of machine you're using. If you're using a CNC machine, you can usually touch the tool off the part. But
Yeah, but okay, but let's not do CNC. We're manually machining. What? Let's say it doesn't matter. Flat or turning could be the same. Let's say it's flat, and we are using a vertical milling machine.
Start off the part.
What?
Start off the part.
You basically, what you're going to do is, most machinists, I'm not going to say all machinists, I don't know, there's usually some tissues around to clean your safety glasses. Safety glasses, usually clean your safety glasses. And it's a very thin tissue. And if you put it in a micrometer, you can tell exactly how thick that paper is. And you put that on the surface and you manually bring down the tool, sliding the paper until the paper stops moving.
yeah.
And that becomes your zero.
I actually worked as a machinist for a year and a half. That's exactly what we did. We took like a little piece of paper, we measured it with like a micrometer, like 3 thou, and then we would just insert that into the program. And 95% of the time, it'd be within 5/10 of where you want.
You got it. You got it. Okay? For a robot application, if you're dealing with very sensitive components where doing any oddball motion of the part is a big issue, you can do similar kinds of things to make sure that you're gripping the part appropriately and not pushing it too hard on the right or the left. Okay? So, anyway, with that introduction, we place the gripper on the pin at the pickup position. Okay, so in that case, we're going to have an equation. Let's go back again and look at that diagram. Essentially, it's going to be the product of Z times T6 times the tool. So that's all going to be there. Instead of OBJ times F, let's call that P. Okay, that's the pin. And then G is going to be what we're calling over here PG. Okay? And so if I want to solve for P, we're going to figure out all these terms in shortly. If we want to solve for P, we pre-multiply both sides of the equation by the inverse of PG. If I post-multiply both sides of the equation by PG inverse. So if I multiply this side of the equation by PG inverse, this disappears. A times A inverse is identity matrix. So essentially this disappears. There I have P, and it's going to be Z T6E times the inverse of PG. You're with me? Okay. Now, we know what PG is going to be depending on what exactly we're doing. So let's take a look at an example. Let's assume for right now that I have a pin, and you arbitrarily have decided that the pin's coordinate system is going to have Z going through the long axis of the pin. Okay, that's a possible location for P. And then you're simply going to say that X and Y is going to represent the flat plane of one end of the pin. So there I have X, Y, and Z. I define that as my coordinate frame associated with the pin P. But then I have my gripper. Okay, that gripper, notice I have a gripper and I've drawn it with the two fingers coming down. And let's assume I want to grip the pin at a distance D from one end of the gripper. If we look at the coordinate frame associated with the gripper, the tool coordinate frame, if we look at it, this is what it should be. Z should be pointing down, because my tool is pointing down. And again, remember, Y is between the two fingers of my gripper. And so essentially, I'm going to have a right-hand coordinate system where X is pointing in this direction, Y is in this direction, and Z is pointing downwards. Okay? So what is PG? All right, what is PG with respect to the pin's coordinate frame? So if the pin's coordinate frame is over here, I need to translate along the Z-axis by minus D, by minus D, and then I've got to rotate about the pin's Y-axis by minus 90 degrees. When I do that, the Z will be pointing downwards, the latest Y is pointing in this way, and I have X pointing in the right direction. If I do that, PG with respect to pin is essentially you just plug that into a rotation matrix rotating about Z. So you get this matrix, which turns out to be 0, 0, minus 1, 0, 1, 0, 1, 0, 0. And we are translating in a minus D direction. So this is the PG with respect to P. But what you're going to see right away is, why bother? Can't I make my life simpler by just deciding on a different pin coordinate frame? What if I decide that the pin's coordinate frame should look like I'm drawing over here? Okay? So this is now what I'm going to call the pin's coordinate frame P. I'm going to say that the X coordinate frame should go along the axis of the pin. I want the Y coordinate frame to be basically through the major diameter of the pin. And then Z should be pointing upwards. So Z is pointing up. X is along the axis of the pin. And I choose my coordinate frame, the origin of this pin's coordinate frame, to be right where I want to grab the pin and squeeze it. Remember, you can define the coordinate frame any place you want. I'm telling you, we're going to define it to be in this location. And so you're going to say, what about the gripper? The gripper is drawn in red over here. And so if we take a look and now draw the various parameters, P is coming from the base coordinate frame. It's going to the center of the pin. E, remember what E? E is the tool coordinate frame. It's the offset from the flange to inside the gripper. And we can pick E to be wherever we want along the approach vector, if you want to call it that, about the z vector. We can pick it wherever we want. And so let's say E is pointing down to the bottom. And so then PG, again, PG is relative to P. So PG can be defined with respect to the center, pointing to the same location where E is. But remember, these are all poses. They're position and orientation. So E and PG aren't just vectors. They have a coordinate frame associated with them. And that coordinate frame has to line up and point in the same direction. Otherwise, we don't get an equation. So if we take a look at that, two things we can do. Let's say it's a pin like that. If I want to come down with my teeth and I want to pick up a pen, whatever you want to call it, typically I'm going to want to have some type of groove in the teeth of the pin. If I want to know exactly where I'm going to hold the pin, I'm going to select and I'm going to pre-machine the teeth of my gripper. And by the way, on the UR5, at least on the grippers we purchased, you can change the teeth. There are removable parts that we can change. And we originally, what we did, and this is quite a ways back, we used 3D printing to create the V shape that we wanted and played with that for a while just to make sure that it worked for us. And then we machined the teeth because the materials used in 3D printing, they don't last very long. But it was good enough to just check everything out. And then we made, you want to make the teeth then out of some hard alloy, 4340, stainless steel. Again, depending, remember those materials get to be pretty pricey. But if you're going to be picking up parts over and over and over again, thousands of times, you know what, if you don't pick a really hard material, it's going to wear away in no time. So again, you want to pick, I think 4340 is a pretty good alloy for this kind of steel, or go to stainless steel if there's an issue with the moisture and humidity in the environment. So notice the other thing, I've picked the teeth so they don't hit the tabletop. Because notice if I have this arrangement, we need to be very careful, because if the teeth hit the tabletop, that's not a good thing, okay? And so it's always a better idea to make sure that you pick the location of picking up the pin such that the teeth don't end up hitting the table surface on which the pin is resting, because tolerances and inaccuracies, ultimately you're going to have issues with the teeth are going to hit the table, and that's going to cause impact. It's going to cause bad things. You don't want to have the robot smashing into the table, even if it is gentle, because you never can predict how this will all play out. So again, notice that E is different depending on where we want E to point to, and PG has to follow it. So here is E going all the way to the end of the teeth, and PG follows it. So PG is basically going to be a coordinate frame that is going to depend on E, E being the tool coordinate frame, and P is the object's coordinate frame. And then PG just connects the two. It is related to the two, and it essentially is going to make sure, remember this is drawn as a vector, but we have to spin the coordinate frames around so that if Z is pointing downwards, PG is also going to, the axis of PG also has to point downwards. Okay, so let's take a look at an example. And you'll understand the example better if I start off with the approach point, PA. PA is, oh, it's 10 o'clock. Guys, you need to tell me. I get so excited here. I lose track of time. I'm 5 minutes over. Sorry about that. Why don't you, I'll pick up on this. Today's Thursday. We'll pick up on this coming Tuesday. This is not going to be a problem on your exam. Everything we've covered until today is going to be covered on your exam. What I'm covered today and this coming Tuesday will not be covered on the exam. After I finish this whole discussion, we're going to move to Jacobians. So not to worry. But again, this particular problem just refreshes your memory about coordinate frames and what they do and what we need to worry about in order to set up a language, if you will, for programming robots to do stuff. Thank you very much.
Practice might it be simpler to define our coordinate frames if the view would be aligned with our gripper?
You can do anything you want. And you're going to see, I'm going to go through some examples, and you can then make your own decisions of how you want things lined up. Okay? Again, I use a pin, but it really depends what you're picking up. And the gripper, it may not be a gripper. It may be a nozzle of something. So again, I don't want to over-specify.
We're generalizing, we want to allow